Earth-based gravity regulates local motion through space-time, imposing limits on relativistic inertia. In contrast, space-field dynamics influence how space-time evolves, allowing for superluminal separation without the need for force-mass increase or boundless energy. Misunderstanding these different regimes can create artificial constraints such as the illusion of infinite mass. As the scientist fine-tunes the experimental setup, the data reveals intriguing insights into the nature of gravity and space-time interaction. Outside, a sleek spacecraft glides effortlessly through the shimmering field, embodying the revolutionary potential of understanding spacefield dynamics. With each breakthrough in analysis, the scientist uncovers new dimensions of how gravity shapes our understanding of motion through space-time. Meanwhile, the astronaut drifts among the stars, representing the boundless opportunities that arise when we transcend conventional limits imposed by gravity. As the scientist shares the remarkable results with the team, enthusiasm fills the room, igniting a collective passion for exploring the unknown. The captivating image of a distant galaxy serves as a reminder of the vast mysteries that await our understanding of spacefield dynamics. The infinite mass illusion versus energy. As discussed, the mass of a spacecraft does not physically increase as its velocity rises. Its rest mass remains constant. What diverges in relativistic formulations is not mass itself, but inertial resistance, the energy required to further accelerate the object. As velocity approaches the speed of light, the required energy asymptotically approaches infinity. This divergence is often misinterpreted as infinite mass, but it is more accurately described as infinite inertia within the relativistic framework. An intuitive analogy is pushing a car uphill. On level ground, the force required is modest. As the incline increases progressively, more force is needed to maintain acceleration. Approaching the speed of light is equivalent to the incline steepening without bound. At light speed, the incline becomes a vertical wall. No finite force can produce further acceleration, not because the car has gained mass, but because the kinematic framework imposes an asymptotic energy barrier. No finite force can produce further acceleration, not because the car has gained mass, but because the kinematic framework imposes an asymptotic energy barrier. Crucially, these equations describe motion within a planetary locally gravitational environment where inertia, force, and acceleration are defined relative to matter-bound reference frames such as Earth. In such environments, gravity is experienced as a force, and zero gravity corresponds to free fall within a gravitational field. In contrast, spacefield gravity, as defined in quantum physics, is not a force arising from mass concentration, but a global expansion dynamic of spacetime itself. In regions of weightlessness, local gravitational coupling approaches zero, allowing inertial resistance defined by relativistic equations to decouple from motion, mediated by the spacefield. Under these conditions, propulsion is not achieved by pushing against mass, but by coupling to directional spacefield expansion, bypassing the relativistic inertia divergence altogether.